or something like that.
No.
Okay, not mine.
That's nice.
Okay, our next speaker is Tobias Grafke. Sorry, I should be able to pronounce that. Metastable atmospheric jets, large deviations for stochastic averaging.
Yeah, thank you for the introduction, and also thank you for the invitation and for the nice organization. So, as was just said, the goal is to talk a bit about metastable atmospheric jets. It was already hinted at a bit at some of the earlier talks. But I'm coming from the perspective of large deviation theory, and in this case also stochastic averaging. And I assume, because this audience is somewhat diverse, that I should introduce into these fields, maybe more so than into atmospheric jets, even though I hope to get to it. I feel that the time limit is much more strictly enforced in the afternoon. But yeah, we will get to atmospheric jets eventually. Okay, so I will start with large deviations. And if you're not so interested in the technical details, I'll hopefully pick you up later. So jumping right in, the prose version of large deviation theory is a situation where the way that a rare event occurs is very predictable, namely that it is dominated by the least unlikely scenario. So that might sound a bit cryptic. So I always give this example. This is a 2D phase portrait of a dynamical system, a 2D dynamical system. I have 2 degrees of freedom, phi and phi dot, some angular variable and the velocity of it. And these streamlines correspond to the deterministic dynamics of the flow. And these are the corresponding equations. So phi is just an angle and phi dot its velocity. And for the velocity equation, you see that there is some restoring force and a friction term. So in essence, this is a pendulum, just because to make it a bit higher stake, I always say this is the motion of a ship on the ocean, the ship rolling motion. So it's only a single degree of freedom of the ship rolling. And you see these 2 points here and here, which basically correspond to the ship in the upright state and to the ship being capsized. And of course, there's another fixed point, which is just the edge state, the saddle point on the edge where it's right on the process of tipping. And you might ask questions like, given that I start with an upright ship, how likely is it, what timescales do I expect to have for the ship to eventually topple over driven by random noise? So in a sense, it's very much a similar setup as we have just seen for much more complex models. Here it's simple because these are just SDEs, 2 degrees of freedom, and additive Gaussian noise. The noise is not very realistic for a ship anyway. So because it's such a small model, instead of just generating a few samples, I can indeed generate millions or billions of samples and just condition on the transition happening and look at the distribution of this. So this is a distribution of transition paths, a distribution of capsizing ships, if you will, starting here and ending here. And what you can tell clearly here, it was also visible in the final figures of Hank's talk, is again here you have this thing, and this is what I mean with this text box, that all the transitions happen in a comparable or similar way. There is a clear channel where they're all moving through. In particular, they're all moving close to this saddle point, but they're all coming from the top left and they're all going to the upper right. And indeed there is, and that's the essence of large deviation theory, some kind of limiting trajectory in the limit where the noise goes to 0 and the limit where the event becomes more rare and rare, that in path space, all of this concentrates around a single trajectory, and that's the right one. So that's the essence here. To make it a bit more formal, from a mathematical perspective, this is how you would introduce it. You have some kind of family of stochastic processes with a parameter epsilon. And if this fulfills a large deviation principle, this is true. So the probability that a sample of my process lies close to an arbitrary path of my choosing, phi, is given by this formula, where, to unpack this, in the inside here, I say the supremum over time of the difference between my sample and my chosen path is bounded by delta, meaning I remain within a delta tube around my given path. This probability scales like an exponential. So these wiggly equals is, I pronounce as scales like. There is a more rigorous meaning, of course, of it. And in the exponent, you have the smallest parameter to the -1 and the functional evaluated at this given trajectory, the arbitrary one of my choosing, which is called the rate function, or maybe if you're more physically inclined, the action. So if this is true, and this is true for a large class of systems, you have a large deviation principle. And why is this useful for the problem that I was showing you is the following. If you have this, then you can easily intuitively deduce a property like follows. The probability of ending up close to y, for example, in the capsized state, given that I start at x, the upright state, also scales like an exponential, but now in the exponent, I need to minimize my action over all paths that connect x to y. Why is that? Because for all of them, this property holds, but the ones that have a larger action are exponentially suppressed against the one that has the minimal action. And you also recognize a lot of classical mechanics, statistical field theory, and so on in it. It kind of like amounts to a saddle point approximation of a path integral. But this is also known in Freightliner theory. So you can make it a bit more rigorous. What I care about is that oftentimes you can find the minimizer itself. I call it phi star, which is the argmin of the rate function. This is the white path that I showed earlier, which will be the one that minimizes the action and therefore maximizes the probability of transition and can be used as a placeholder. So this can be made precise for SDEs in the small noise limit. This is called Freightliner theory, where you have a closed explicit form of your action. You can write it as a time integral over a Lagrangian, which is nice because then this instanton that I talked earlier, this maximum likelihood pathway, can also be obtained by solving the corresponding Hamilton's equations. So this is classical mechanics. This is a minimizer of an action with a Lagrangian eigenvalence that formulated as a Hamiltonian. This is a bit more general, maybe because these Lagrangians often look weird. They don't have necessarily a quadratic term in the phi dot, so you need to do a full Fenchel-Legendre transform. But solving this equation is the same as solving the optimization problem. So if all of this was too much detail, maybe then here is a summary of what I just said, and that's only the effective thing that I want to do. The main problem that I'm facing is, given a stochastic process, I have an action. Given this action, I want to find a minimizer that does a certain thing. For example, the ship toppling or the pendulum flipping over once. So I need to minimize it over all trajectories that do what I want. And then the minimal one is useful for me, for example, for estimating the probability of the event happening. If I know the instanton, this minimizer itself, I can estimate at least the scaling of the probability. But I can also look at how the event itself happens, because exponentially likely, all of the transition trajectories will cluster around the white one in the limit. All the other ones become unimportant in comparison. There are, of course, complications and technical notes to this, but that's the story. If I'm interested in the limiting probability, then I will also get the limiting transition trajectory. And even more to it, by solving this optimization problem, we also get out something like, okay, what was the actual value of the noise that drove me to it? So you can invert the question, say, how would I need to force my system in order to facilitate the transition? Okay, so this is standard theory. I'm going to continue with standard theory, but of a different kind, because what I want to apply this on is stochastic averaging. So we've already heard a lot of times that maybe a clean scenario such as this one is never true in climate, maybe in some examples. Here I'm talking about a situation where I have a large time-scale separation and a clear picture of which degrees of freedom are slow compared to the others. So these would be the equations. I have x dot equals f being slow and y being my fast variable, where alpha is the time-scale separation parameter. If alpha becomes small, then y evolves much faster than x. And the things that are traditionally done with it mostly is the first one that I have in the list here. I want to write an effective equation for the slow degrees of freedom only under some closure assumptions, and then characterize its attractors. This is basically a law of large number type argument for the stochastic average. You can also think one level higher and say, what are the effects of the stochastic noise on top of it? So taking out everything that is average, what do I expect for fluctuations? There will be squared alpha in size, but what exactly would be their covariance and so on. This is the Relanoff central limit theorem. But then lastly, and maybe what I'm most interested in, what's the extreme long time behavior? If the effective dynamics have multiple attractors, I eventually get transitions between them driven by the noise, where the noise is not a stochastic term in the slow equation itself, it's coming effectively from the fast one. And that's a large deviation principle, but for stochastic averaging. So this has been worked out in detail. I'll tell you first this law of large number result, because it's very intuitive and easy to see. So that's just a copy of the equation, a slow one and a fast one. And the effective equation is basically just averaging the right-hand side over variables for y under the assumption that I integrate a fast equation for a fixed y. Effectively, what I'm saying is, for the fast equation, the slow one is so slow that I can assume it stationary. Then let y equilibrate, and that's the measure that I need to integrate my slow degrees of freedom over. So that's basically just averaging over the equilibrium distribution of y for a given x. That would be the average in general terms, the average mode equation. So let me do a simple example. The simplest non-trivial example that we could come up with, and that's nice because you can compute a lot of things explicitly. The slow equation has a quadratic input of the fast one, and the fast equation is linear. So there is a linear restoring term gamma, but it does depend on the slope variable, but it's linear in y. Why is that easy? Because we can, for the linear equation, we can compute the covariance explicitly. Sigma squared over 2 gamma is the covariance of an Ornstein-Uhlenbeck process. And then I just need to plug this in here, because in the large timescale separation limit, the only thing that I do is replace this y squared instantaneous by its expectation under a fixed x. So this is what the law of large number looks like. Instead of y squared, I write sigma squared over 2 gamma bar. So for a given choice of gamma of x, this might be a phase portrait for 2D variables here. And then I can again identify multiple fixed points in this scenario. So then it makes sense to ask the question, how do transition happen between those, which cannot be answered on this level because this is purely deterministic. There is nothing that can drive a transition. If I'm here, I will slide on here. If I'm here, I will slide on there. And there is a saddle point in the middle as well. But of course, one thing that you could do, and it's an important thing to do, is to compute heteroclinic orbits connecting the fixed points. I mean, first, because clearly this is a candidate for a possible transition, but it's a bit deeper than that. If the system was reversible, if you would have a detailed balance condition, this would be the instanton trajectory that I showed you earlier. It's not in general, but in the special case of reversibility, it is. And if you're close to reversibility, maybe you can expect that it happens in a similar way. Okay, so the intuition here is the following. The law of large number describes the average behavior. So on the order 1 slow timescale, we will converge to attractors. Then the central limit theorem just describes order squared alpha amplitude fluctuations around these fixed points. But if there are multiple attractors, given enough time, and that's a lot of time, it's e to the alpha to the -1 time, fluctuations eventually will lead to a transition with the same argument that I did easier before for SDE cases, only that here we're not in the SDE situation, but in the stochastic average setup. And large deviation theory is the correct framework for this. And this has also been worked out. And that's maybe a bit, I mean, I guess impossible to understand if you don't read the paper. What you get out is the Hamiltonian of the large deviation principle that I showed you earlier. That's the Legendre transform of the Lagrangian, just that the Lagrangian doesn't have a nice form. This one is also not nice because it contains both an expectation and a time average. But that is the large deviation Hamiltonian for the slow fast system in the large timescale separation. So there is no general explicit form except for this equation, which is rather ignorant. But for the simple example that I showed you, you can compute it explicitly. So I have my slow equation, I have my fast equation, and the law of large number. And I can also write down this Hamiltonian exactly. So if you have a bit of experience on how to interpret this, you will see that if it would be a Gaussian process, this must be quadratic in the conjugate momentum in P. It is not, it's here under the square, and it's a bit of a weird thing, but you can write it down, compute it, and you can even then solve the Hamilton-Jacobi equations to get this most likely trajectory out of it. And that's the red line for the transition from the upper right one to the lower left one. So this portion will be shared because once you've crossed the separatrix at the saddle point, they will all coincide anyway. But the uphill climbing motion is markedly different than the one that you would naively maybe expect from the reversible system. Lastly, one thing that you could think of doing is instead say, I have my law of large number, I just need stochastic noise on top of it. Why not take the stochastic noise that comes out of the central limit theorem as a Gaussian approximation? I can construct an SDE, a Gaussian SDE, with the law of large number plus the covariance of the central limit theorem random noise, which effectively amounts to truncating this Hamiltonian at second order in P. That's the closest Gaussian process mimicking the rare transitions of the stochastic average one. This yields yet another different trajectory. And I guess the only point that I'm making is that in general, all of them are different. The right one is the solid one. It's in general hard to compute. You can approximate it maybe with a dashed one, even though I don't know of any quantitative guarantee that it is close in any form. Or you can look at the Hydroclinic orbit for the reversible process. So why am I telling you all of this? Is the following situation. 5 minutes for jet. I'm looking at systems such as Jupiter, where you have very clearly established jets. On Earth, I guess it's much less clear. And that's visible, for example, in this nice figure where you have, as a function of latitude, the zonally averaged velocity field somewhere in the upper atmosphere, where we see large positive or large negative values corresponding to eastward or westward jets. And if you're looking closely, you see that this is actually not a single line, but two lines. And the reason for that is that there's two measurements, one from Voyager in 79 and one from Cassini in 2000, meaning that between those two lines, which are basically overlapping, 20 years have passed, or a bit more than 20 years have passed. So these jets are stable on extremely long timescales. On the other hand, if I understand correctly, it is suspected that Jupiter did lose a jet sometime in its past. So the question is, what's the lifetime, what's the metastability of these jet solutions? I'm not going to answer this question in full, but the comment that I want to make is that the most primitive model to describe that is the model that we've seen now a few times, 2D stochastically forced barotropic beta plane turbulence. This is 2D Navier-Stokes plus beta term, which is Coriolis force. I have linear friction here as well, so that differs from the analysis talks that we had earlier. I can then go ahead and say I want to zonally average them. I define a capital U variable that's basically the X average of my instantaneous velocity field, and then expand in those variables. So I have a mean, a zonal mean, plus turbulent fluctuations appropriately scaled with my smallest parameter that occurs here. And then in this new split set of coordinates, I drop the nonlinear interactions between the fluctuating terms. This is a well-known procedure. It's called the quasi-linear approximation, and the resulting equations that you get are these. An evolution equation for the jet profile, which has as input a Reynolds stress term coming from from fluctuations that are here, which is linear by construction. And if you look at that, the beautiful part about it is exactly that this equation is linear by construction. This equation has a quadratic influence of my fast degrees of freedom on the slope. So it's exactly of the example form that I showed earlier, except that it's a PDE, so there is a big leap of faith as well if you want them jumping from 2 dimensions to infinitely many. So exactly this is what happens, and you can write down a closed form model. This is just a copy of the equations before, but in the alpha to 0 limit, I can replace the quadratic term with its expectation, and I can write the fast equation as a virtual fast equation under a constant U. So I now have like an omega tilde that behaves with a non-evolving capital U. That's the instantaneous one from the above. And then I obtain a closed model that's basically integrating forward my jet profile under the equilibrated turbulent fast fluctuations, which I get from solving a Lyapunov equation on the fast degrees of freedom, because the fast equation is linear, even though I cannot write down sigma squared over 2 gamma. Instead, it's a solution of a Lyapunov equation, where the gamma is a linear operator. That's a bit ugly, but it's linear. And indeed, if you solve this system and wait for it to equilibrate to fixed points, you get jet-like solutions. All of this is well known, but it compares nicely against fully nonlinear systems. So now the last part that I need to do in 2 minutes or something, you didn't stand up yet, so maybe I'm good, is you can use this.
I'm new to it, I'm new.
Well, I have 5 minutes after you stand up. No. Okay, we can use this to look at this simplified system to compute the fixed points. And indeed, we do find parameter ranges for which multiple fixed points exist. So you have this situation where you have more than one stable fixed point. For example, in this case, a 4-jet and a 5-jet locally stable solution. So I'm just integrating forward this law of large number equation that I was talking earlier about, and I get both a 4-jet and a 5-jet solution locally stable. So in some kind of sketch of a landscape, I could say there is a 5-jet basin of attraction and a 4-jet basin of attraction with a separatrix between them. And already on this level, I can ask questions like, what does the edge look like? And in particular, what does the saddle point on the edge look like? Which should also be a fixed point of the law of large number limiting coarse-grained dynamics, just an unstable one. And this can be computed, and here I show it for this to that transition, where in light blue you see the 5-jet, which is the one that I have here, and in dark blue you see on top of it one of the jets being slightly smaller to a degree exactly such that If it would be even smaller, it would disappear. And if it would be slightly bigger, it would restore the fifth jet. So this is the stable solution on the edge between 4 or 5 jets in the effective model for the quasi-linear approximation. And the last thing that I wanted to show you is you can also compute these hydroclinic orbits from 5 jet to edge and from edge to 4 jet, which looks like this. So you can imagine this as being starting from the edge. This is how you would slide downwards towards the 5 jet, and this is how you would slide downwards towards the 4 jet. Or you can view it as a single orbit connecting 5 to 4 jets, going through the edge, which would be the transition trajectory if the system would be in detent balance, which it is not. The problem is that getting the full instantonic trajectory out of this very implicit Hamiltonian is basically prohibitive, or is very difficult even for high dimensional systems, but in particular in this PDE case. So that's the thing that I can show you. So to summarize, we can reason about metastability via these sample path large deviations in very generic situations. And the specific situation, apart from the introduction that I showed you, is how to do that for stochastic averaging, where there exists a framework that for some simple cases allows you to write down a closed form. But via that, you can compute probabilities of transitioning and get knowledge about times and so on. But this is applicable to many more systems, and here are a few that I'm looking at, such as like fiber optics, climate, plasma, the jets we just saw. And with this, I thank you for your attention.
Valeria?
Yes, I have a question. Assume you have your bistable system and you have a reasonable estimate of your edge state. Now you add noise into the system. Let's say a particularly boring noise, a simple elliptic process. And so on. You reduce the noise and you see transitions. And
sorry, you mean you add noise to which dynamics? To the average dynamics?
Yeah, yes, let's say to the average.
Okay.
Anyway, you have a system with noise.
Yeah.
It's without noise, it's multi-stable. You have noise, it's metastable. You observe transition.
Mm-hmm.
You observe Cramer's law, so everything works fine. Then you plot on your reduced space, and you notice that this transition do not go through the edge state.
Yeah, I guess.
What would be your take on this? Because
so, I mean, I didn't explicitly say it, whether there is or isn't a guarantee to cross the separatrix at the saddle point. And I don't think in general it's true. We encounter multiple scenarios where a transition happens where you don't necessarily go through the saddle when you have exotic noise. If you have boring noise, it's easier. We had this discussion earlier a bit. You can maybe still construct edge cases, but I would think in general you would cross the separatrix at the saddle in the low noise limit. But if you have finite noise, there might be entropic arguments that destroy everything, right?
Sure, yes.
So that was maybe the scenario that you were painting anyway. If you have any kind of finite noise, these limiting results might apply so late that they're no longer relevant.
Yes. No, I'm thinking in the case, assuming you take the limit, would you expect anyway to go to the edge state? Or if the noise is, say, elliptic additive or something?
So, I mean, I think in general it does,
Okay.
but that's just a heuristic. And I don't think it's easy to prove that it must always.
Okay, good, thanks.
So some further questions. Okay, I have a follow-up question to that.
Sure.
So I mean, I think what is true probably rigorously is the moment. I mean, you're behind the saddle, and you somehow go on the Hydroclinic orbit. You will follow that one, because that's the best way to go from this moment on.
Across the separatrix, you can just slide down wherever you are, not necessarily from the saddle, right? You don't need any noise anymore.
But probably will be somehow channeled into it or something like it.
No, not necessarily. But when I think it matters at what point you cross the separatrix, because once you cross the separatrix, you will be deterministically decaying, and it need not come close to the saddle. I think that's true.
Okay.
So thank you first of all for the very nice talk. Yes. So all right, when you want to compute the instanton, right? You briefly mentioned that we can obtain that using the Hamilton-Jacobi equation.
This is the Hamilton's equation, it's not the Hamilton-Jacobi.
Right? Hamilton's equation. So now, if I want to compute that like for instance, like by forcing the low mode, the slow mode instead of forcing the high mode.
Sure.
So you will end up with a similar.
This is not a problem now.
Yeah.
So it's only because of the application that we only force the fast degrees of freedom, but I don't think it makes a difference if you have the slow as well. If you have stochasticity on both degrees of freedom.
No, not on both, but just on the slow.
Well, then what about the fast one? It's just deterministic.
Yeah, the fast, but the fast could be still fast, like while being deterministic.
Sure. If it's not chaotic, I don't expect that. I mean,
no, it has to be. If it's chaotic, yeah. So
yeah, I mean, with chaos, I think everything becomes different.
Yes.
So I'm not sure whether there are rigorous theorems for every possible scenario. I know that there are many distinctions that are made between what depends on what. For example, whether the fast depends on the slow.
Let's see, like if I pick up, for instance, let's say I pick up the QG example again.
Yeah.
Okay. So I place the QG example in a chaotic regime.
Right.
But now I'm going to force like some low mode.
Yes.
Right. Stochastically. So then the fast modes are intrinsically produced. They don't need my noise, right?
Yeah. I see what you mean.
So in that case, like the averaging, I mean, all the CLT, all of that must be very difficult to derive, correct?
Yeah, I think it's much more difficult in that case. You need to know the SRB measure or something of the fast process.
Yes.
So I'm not sure whether you can get this in general, but
Especially for PDs. Right?
if I do quasi-linear theory, what you're saying is not working, but you are saying the fast degrees of freedom should be non-linear but chaotic.
Yeah.
Then you would need this. Yeah. Then you would need the SRB method. I don't think it has been attempted, and it's probably difficult in general.
Okay.
Would it be possible to assess whether the large deviation principle itself is satisfied for all those different cases?
So for this case, it's always satisfied in the limit of infinite timescale separation.
What does that mean for the scenarios like
For the chaotic one, I don't have the expertise to tell you, but I think so. I mean, you need to have some property of the fast process, but that has to do with its chaotic nature, right? And if you have that, I think it should be there. Because somehow the bigger the timescale separation, the less, sorry?
like mixing property?
Yeah, I think so. But I don't know the specifics, but it must be like that. And I think then in the limit of infinite timescale separation, you should have something. Just by intuition that, I mean, it must become more and more rare because the fluctuations are less and less strong.
In the landscape of the 4 and 5 jets that we drew, there was just one saddle point, right?
One that we found?
Yeah, so can you be sure that there are not other gates to move from 4 to 5?
So there could be in general. The way of finding them is the same problem of finding a global minimizer out of a set of local minimizers. So I'm not sure whether that you have any guarantees. You probably don't. So you can try edge tracking on various different initial points and observe that you always converge to the same one. One important and maybe interesting thing to note here is that topologically you might imagine, I mean, red and blue, whatever the colors exactly mean eastward, westward. There is at least one other thing that you could imagine happening, namely 2 red ones merging instead of 2 blue ones merging. And it's only this one that is selected and the other one never. And there is no 1 degree of freedom unstable saddle point in the other direction where 2 reds meet, where there's probably some physical meaning to that. But yeah, this is exactly what we looked at. Is it exactly symmetric between the two? And it is not. But we didn't find any other saddle point in this case. But also it is a problem in general because you cannot guarantee it.
Okay, so let's thank the speaker again. And time for coffee break, and we reconvene at when? Let me check. At 3:30.